The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next speaker is Ted Moffatt from the University of New Brunswick.
Good morning. My name is Ted Moffatt. I'm a postdoctoral research fellow at the University of New Brunswick. I'll be completing my postdoc in the coming months and moving to the Toronto, Ontario area. So if anyone is, and I'll be seeking employment, so if anyone's looking to hire, or if you know of anyone, please let me know. And again, if this presentation doesn't go well, you might not want to talk to me. So I'd like to start off by acknowledging my co-authors, Mike Thomas, Andrew Fahim, and Herwing Lopez. And I'm going to be looking at the effect of cracked high-performance concrete exposed to a harsh marine environment. Now, when designing infrastructure to withstand sort of 100-plus years, there's a number of issues that we must take into account. We must ensure it's mechanically sound to withstand the loads being applied on the structure, but also durable enough to withstand the harsh environment in which it is placed. And I think you'll all agree that corrosion is a major issue affecting our infrastructure at the moment. Now, it's inevitable that throughout the service life of our structures, cracking will initiate. However, it's our job to minimize cracking. Now, the bridge pictured here is the Confederation Bridge. It's a fixed link between the province of New Brunswick and Prince Edward Island on the eastern part of Canada. It was constructed 20 years ago and was the first use of high-performance concrete in North America. Now, corrosion, as you're probably all well aware, is the leading cause of premature deterioration of concrete structures in North America. And it's not surprising, as our infrastructure is exposed to road salts this time of year, and structures like the Confederation Bridge or structures on the West Coast are exposed to seawater on a daily basis. Now, fortunately for us, there are a number of ways in which we can mitigate corrosion. We can start off by looking at non-chloride-based deicers. Potassium acetate, for example, is a biodegradable non-chloride-based deicer used on airport runways. However, the cost is significantly higher than rock salts. We can use a number of other mitigation techniques, membranes and sealers, or densifying the matrix of our concrete through the use of ultra-high or high-performance concrete, ensuring sufficient cover, using non-iron-based metals such as stainless steels, coatings on our steel such as epoxy coating reinforcement, the use of corrosion inhibitors, and anodes and cathodic protection. And for the sort of remainder of this presentation, I'm going to be mainly focusing sort of on the effect of cracking in high-performance concrete and mitigating it through SCMs and corrosion inhibitors. Now, there's a number of mechanisms associated with sort of cracking in concrete, and it really has to do with the matrix surrounding the steel. If we look at a high permeable concrete, say a Portland cement with a water cementing ratio of 0.5, the anodic region will be satisfied through the dissolution of iron at the foot of this crack through the penetration of chlorides. And the cathodic reaction will also be satisfied through the penetration of moisture and oxygen throughout the matrix of the concrete. And this more or less results in generalized corrosion over the length of our bar. Now, as we densify the matrix within our concrete, say we decrease the water cementing ratio or we add SCMs, the cathodic and anodic regions will become closer together. So we'll form more so microcell corrosion, and this will more so lead to pitting corrosion. So if we sort of look at the effect of high-performance concrete, a low water cementing ratio, whether it be through corrosion inhibitors and supplementary cementing materials, this will result in microcell corrosion where the anodic and cathodic reactions are more or less adjacent to each other, and this will lead to pitting corrosion. So this study looked at the effect of high-performance concrete and the synergistic effect between supplementary cementing materials and corrosion inhibitors. Now, fly ash and silica fume, as you know, are ideal materials for one another in ternary binders because the fly ash compensates for the low workability of silica fume, and silica fume compensates for the low early strength of fly ash. Now, the two are also beneficial in mitigating chloride penetration. Some of our latest results that we've published, Andrew Fahim published some results recently in an ACI SP, where we found that there was a marked reduction in the penetration of chloride ions in concrete exposed to a harsh marine environment for 27 years. And this certainly outweighs any debate associated with sort of arguments regarding chloride threshold sort of for standard black steel. Some of the other results we also published, the figure on the right, is the performance of high volume fly ash exposed to a harsh marine environment for 25 years. And again, we're seeing a marked reduction in chloride penetration in the use of fly ash, upwards of replacement levels of 56 to 58%. Now, the study also looked at the effect of corrosion inhibitors. We looked at a calcium nitrite inhibitor. If you're unfamiliar, it's an inorganic corrosion inhibitor, and it repassivates the dense ferric oxide layer that may be destroyed through chloride ion penetration. So this sort of repassivates that sort of hole in the green layer you can see in the top right-hand figure. The next corrosion inhibitor we looked at was a disodium tetrapropenyl succinate. This is an organic corrosion inhibitor. More or less densifies the matrix, reduces the permeability. However, in the literature has been showed by many to possibly reduce the compressive strength anywhere from 15 to 35%. Now, this admixture contains an air-entrained admixture, so in some cases a defoaming admixture may need to be used in order to ensure the air content is maintained sort of around 6 to 8% in environments such as Treat Island. Now, Treat Island is an exposure site located off the coast of Eastport, Maine, more or less on the border of Canada and the US. Let's see if this video. So the site was initiated in 1935. At the time, President Roosevelt funded a project known as the Passamaquoddy Bay Tidal Project. The Passamaquoddy Bay here runs into the Bay of Fundy, and it's world renowned as having the highest tides in the world. Depending on the moon, these tides range anywhere from 18 to 26 feet. So in 1935, it was intended to dam the Passamaquoddy Bay. These tides generate an immense amount of energy, so the goal was to harness this energy in order to generate power for sort of the area in around Eastport and sort of a large area of Maine. It's one of the harshest concrete environments in the world. It's exposed to, on average, 100 to 160 freeze-thaw cycles a year. The water temperature here more or less doesn't change year-round. It's around 4 to 6 degrees Celsius. This video was taken, I visited the site last Monday morning, so the temperature in the morning was minus 10 degrees Celsius, and then in the afternoon, sort of, it was a nice spring day, heated up to 5 degrees Celsius. So we have sort of a freeze-thaw cycle occurring there. I'll try to stop it. So it's located more or less on the border of Canada and the U.S., 2 hours south of where I live in Fredericton, New Brunswick. And we have sort of a mid-tide wharf where a number of concrete specimens are placed, and also a number of specimens are placed on the beach because the condition of the mid-tide period doesn't look like how it does on the front of Concrete Durability, which was published back in 2000. Unfortunately, the harsh marine environment has taken its toll on the dock. So the results I'm going to be presenting today look at two different studies, more or less looking at the effect of the interaction between corrosion inhibitors, fly ash, silica fume, and its effect on corrosion. So the first study looked at the synergistic effect between fly ash of various replacement levels, 20 and 40%, in addition to corrosion inhibitors. We used a high-performance concrete, so a Portland cement blended with 8% silica fume, and we looked at 9 different mixed combinations. I designate 2 to 5 as double combinations, so this contained either Portland cement and fly ash, or Portland cement and a corrosion inhibitor, and then triple combinations, ternary binder containing Portland cement, silica fume, fly ash, and a corrosion inhibitor. We cast concrete beams, duplicate beams for each mixer. So these 2 beams, the top and bottom, are of the same mixture, and we applied a loading frame to these beams in order to keep the beams under constant flexion in order to open a crack of 0.25 millimeters above a black steel bar on the top and bottom, and a cover of 1 inch above those 2. These beams were cast at UMB, cured for 28 days, shipped to Eastport, Maine, where they were then placed on a boat and shipped out to Treat Island. They were placed at the high tide level in order to maximize the exposure of oxygen and moisture, which are 2 constituents required to initiate and sustain corrosion. So So just showing this is the high tide level. These blocks here further down the beach, we do look at a number of durability issues. These are large 450-pound ASR blocks that, again, were cast at UMB and shipped to the island. If we look at sort of some of the mechanical properties and diffusion coefficients, it's not surprising that the presence of fly ash over time is shown to increase compressive strength. However, the presence of corrosion inhibitors in some cases actually decrease the compressive strength over time. However, the synergistic effect between fly ash and these corrosion inhibitors is shown to produce a marked reduction in chloride penetration. This is supported by looking at chloride penetration profiles in accordance with ASTM C1556 after 1 year. And really there's no beneficial effect in using corrosion inhibitors by themselves, as shown on the figure on the left-hand side. But with the addition of either 20 or 40% fly ash, we see a marked reduction in comparison to the control. We conducted both half-cell and linear polarization corrosion rate monitoring on a yearly basis. And again, these figures sort of complement the chloride profiles, which I showed in the previous figure. Sort of corrosion inhibitors by themselves sort of were not shown in this case to mitigate corrosion. However, in collaboration or in conjunction with fly ash, they were shown to sort of significantly reduce, if not mitigate, corrosion. This is also supported by corrosion rate monitoring. If we sort of look at the condition of these beams after 7 years, this is the Portland cement control. So originally the flexure of the loading frame produced a transverse crack. Sort of, apologize, it's somewhat difficult to see, but the transverse crack is here. And then over time, as corrosion is initiated, a longitudinal crack is formed. Longitudinal cracks are very detrimental because more so of the area over the steel is exposed. If we look at after 7 years of a beam sort of only containing a calcium inhibitor, DTS in this case, again, it's sort of a little more difficult to see. I've tried to highlight it. We have a transverse crack, and then over time, a longitudinal crack is formed. Now, the second half of the presentation will more so be focusing on the effect of construction joints. In this case, sort of a number of variables were studied. The effect of water cementing ratio, fly ash content. In this case, only a calcium nitrite inhibitor was studied at 3 different dosages, and then the effect of crack width and how it affects corrosion. Again, the same Portland cement, fly ash, and properties were maintained similar to the previous study. So in this case, small little sort of plaques were cast with a 1-inch cover. The bottom half was cast on day 0, then a shim was placed of various thicknesses, and then 24 hours later, in order to create this construction joint, the second half of the sort of specimen was cast. Now the next couple slides will sort of show a library of data, and I'll try to summarize as best as I can. Sort of the figures along the top row are at the lowest water cementing ratio of 0.29, and then the bottom are at a 0.45, and then we have varying levels of fly ash, and then the different colors in each figure represent the level of CNI used. So it's not surprising at a high water cementing ratio, if I pull your attention to the bottom left-hand figure, regardless of the presence of CNI, there's no effect in mitigating corrosion. However, there's a marked reduction in decreasing the corrosion rate as we decrease the water cementing ratio to 0.37 and 0.29. And then if we shift our attention over to the right, this reduction is even more increased through the presence of fly ash. Now, what about the effect of cracking? It's not surprising, again, bottom left-hand figure, that we have a significant amount of corrosion really after only 2 or 3 years, and it's not reduced through the use of CNI. However, as we decrease the water cementing ratio again and increase the level of fly ash, this reduction is significantly increased. And then finally, as we sort of open up the crack even more, there's really not much difference in comparison to a crack of 0.25 and 0.5 in this study. Again, CNI is shown to have really no effect in a specimen without fly ash. However, the sort of combination with fly ash and CNI really produces a marked reduction in penetration. And after 7 years, in many cases with a replacement level or a dosage of 25 liters per cubic meter, CNI is very effective in mitigating corrosion. I sort of talked about the mechanism associated with corrosion, sort of whether it be forming sort of generalized corrosion over the length of the bar, or pitting corrosion. And here are pictures of some of the beams sort of extracted out of these plaques after 7 years. So here I'm showing a water cementing ratio of 0.29 with no fly ash or CNI on the left image, and then the presence of 40% fly ash and CNI on the right. And I apologize, the pictures are not the easiest to see. However, what we're seeing is at a low water cementing ratio, the 2 bars pictured here and the 2 bars pictured there, I mean, they're in pristine condition. There's no signs of pitting corrosion or generalized corrosion. However, as the cracks are opened, we begin to form sort of pits underneath the area of the cracks. Now, if we increase the water cementing ratio to 0.37, so we're producing sort of a more permeable concrete, so in this case, the anodic and cathodic regions are sort of getting further away from each other, we're forming more so generalized corrosion, so not so much pitting corrosion, but generalized corrosion over the length of the bar. And if we look even further at a concrete, sort of a low permeable concrete, sort of compared to the other water cementing ratios, again, we really don't have pitting corrosion in this case, more so generalized corrosion over the bar. And again, I apologize, it's difficult to see, but we have sort of a significant amount of generalized corrosion in these cases. So in closing, I've tried to sort of put a few takeaway points in bold. Certainly if we look at compressive strength and mechanical properties, high-performance concrete is significantly influenced by the presence of corrosion inhibitors and SEMs. The permeability and corrosion rate are reduced through the use more so fly ash than corrosion inhibitor. However, sort of the effect between the two is very effective, or the combination of the two is very effective in mitigating the corrosion rate. And really there's more so of a marked reduction in corrosion rate when decreasing the water cementing ratio than increasing the corrosion inhibitor content. And really we didn't find too much of a difference between whether we had a crack opening of 0.25 millimeters or 0.5. And based on sort of all the work presented within this presentation, the combination that performed the best, whether it be in the sort of crack beam samples that I showed in the first half of the presentation or these small little plaques in the second half, the best performance was 40% fly ash and a high dosage of CNI. Finally, if you'd like to contact me about a job, I've included my email and phone number there. Thank you.
Are there any non-employment related questions for Ted? Although I can't blame you for trying.
Yeah, nice paper. One question I've got, I mean, it seems like everybody's always looking at the top end of the crack size and going up, like 0.25 millimeters and 0.5 millimeters. But with the use of lightweight sands and shrinkage-reducing admixtures and maybe a little bit better steel placement, we should be able to get cracks lower than that in size. And what effect did they? I have no doubt that, and that's for you and the previous speaker, that 0.25 and up, there's not much of a difference. But what about 0.25 and down?
I can't answer that question because so this project was initiated sort of before I began my master's, and I sort of adopted it sort of throughout my master's and PhD, and it was sort of motivated based on sort of work being done on the Confederation Bridge, and these were sort of, questions posed to us from them, and they sort of set the variables for the research. So, thanks.
Thank you very much.